Why ever use the principle of least action?
So now we have our general approach and the modern way of writing the principle, so let's apply it to a simple example to see why it works.
Let's say I throw this ball straight up in the air. So it goes from some start point to, say, a different end point in a certain amount of time. Now, if we call the height of the ball y of t, then we can plot these 2 points like so. And then we can imagine infinitely many possible trajectories that could connect these 2 points. Some go a little higher, some lower, some have wiggles, others don't. The only condition is that all paths must have the same start and end point and the same amount of time elapsed between them.
So if we rearrange this, we find that the path that satisfies the principle of least action is the one that obeys F equals ma. In other words, the principle of least action is equivalent to Newton's second law. So with this single principle, you could suddenly describe everything from light reflecting and refracting to the swinging of a pendulum clock, to planets orbiting the sun and stars orbiting the core of the galaxy. What used to be viewed as entirely separate fields of physics were now all unified under a single, simple rule.
Why ever use the principle of least action? Well, that's because Euler and Lagrange came up with a way to make all of this super simple. So all you have to do now, if you want to solve any mechanics problem, is you just write down the kinetic and potential energy, and you plug it into this equation, and you're done. And that becomes extremely powerful.
But with the Lagrangian approach, you have this machine crank out the principle of least action on it, and you get the right equation to motion, and you don't have to be a good physicist. That as a math guy, I can do physics thanks to Lagrange and Euler.